Welcome to the Mechanics of Materials podcast from Imperial College London. Today we are talking with Dr. Dimitrios Bikos, a postdoc here at Imperial. We'll let Dimitrios introduce himself.
Hello, Michael. I'm Dimitrios Bikos, a postdoctoral research associate at the Department of Mechanical Engineering here at Imperial College London. I have been part of the Imperial College community for the past 6 years, focusing my research around the characterization of multi-phase composite materials. My research has been driven by my curiosity to understand how the microstructure of multi-phase materials influences their mechanical performance.
Excellent. And what exactly is your background?
I completed my undergraduate degree in mechanical engineering at Aristotle University of Thessaloniki in Greece, specializing in structural integrity. During my studies, I developed an interest in the mechanics of materials and trying to understand how external loads affect structures. This led me to a final year project focusing on optimizing parabolic lift springs, which are part of a suspension system in heavy-duty truck vehicles, using finite element methods. My research aimed to reduce the weight of these springs while maintaining a constant tolerance in the fatigue. The outcome of this project showed the potential of a 50% reduction in weight in certain group of lift springs. So then, in 2017, I joined Imperial College to do my PhD in mechanical engineering. The project of my PhD was in collaboration with 4 academics, Maria Karalabidis, Yannis Hardaloupas, Mark Mason, and Felipa Khan, from 3 different divisions in our department, which are the mechanics of materials, thermofluids, and tribology. And we had another PhD student working in the same project with me. And in this project, we investigated the effect of macroaeration on mechanical, thermal, and tribological properties of chocolate and their impact on food oral processing. The project was funded by Nestle, and it was aligned with the government's needs to reduce the content of healthy sensitive nutrients, leading the industry to modify their product formulations, but at the same time aim to control or even improve the sensory aspect of their products. The outcome of this collaborative project was a computational tool which links chocolate composition with the mechanical, thermal, and tribological breakdown of chocolate, which is happening during oral processing, and shed insights on how food structure affects their sensory perception.
So Dimitrios, where do you work now and who are you working with inside the department?
So in 2022, I completed my PhD and joined Soraya's Pimena's group, which deals with research around fiber reinforced composite materials. And it's been a year and a half now that I'm a postdoc in this group and part of a large project called NextCom, which aims to develop the next generation fiber reinforced composite materials for high performance application, which exhibits superior mechanical properties under longitudinal compressive loading.
What brought you to this research area?
So the reason that I'm working on this area is twofold. The first regards my interest around the characterization of multi-phase composite systems and the microstructures and how changes at macroscopic level affect the material at real-life scale. This is something that always fascinates me. I like to think that the microstructure is the intermediate link between manufacturing process and material properties. The way materials, in other words, is manufactured will affect its microstructure, and in turn the way the material is structured will affect its behavior under external loads. Understanding this chain of events is the way to develop optimized advanced composite materials. Being part of a larger group of academics and researchers is the other. It's really exciting to collaborate with so many people from different disciplines, aiming to tackle a real-life problem and see the contribution of each member to the ultimate goal. In my little academic experience, I have noticed that research for different fields think and approach each problem differently. And this actually really develops your perspective and helps you have a better idea around the problem. It's really common in real-life problems that the solution proposed from one field have a negative impact on the other. Therefore, having a holistic approach to the problem is usually the way to go.
Now, you mentioned just a moment ago that it's exciting to collaborate to approach real-world problems. So what would you say are the primary real-world problems that your research is aimed at?
Although the main focus of the project is to improve the performance of fiber-reinforced composites, the topic is aligned with government's goal to move to net zero through the development of new lightweight and optimized composite structures. Optimizing the composite structure, we can achieve an improvement in the lifespan and the energy efficiency of the material. This is particularly important for the transportation sector, where the development of new improved lightweight structure will assist the energy transition from the current one to the more sustainable alternatives. In addition, during the project, we had actually parallel activities such as short-term internships and student projects, where the sustainability of the composite constituents was also considered. Note that our project course activities include the development of new composite constituents, new composite architectures, and propose advanced numerical methods and experimental protocols to improve the performance of the composite.
So you've laid out several goals. What are some of the difficulties that you'll face when trying to achieve these goals?
So one of the main challenges in the literature is the issue of the computational cost of these macromechanical models. This originates from the complexity of the macrostructure of these materials, which results to computational heavy models when we try actually to reconstruct the real geometry on a virtual environment. To overcome this issue, most macromechanical models in the literature either assume a very simplified macrostructure or consider volumes of material that are too small to be considered representative. Often this simplification can provide misleading results and conclusions about the behavior of the composite. Fortunately, when we investigate and we focus on the effect of realistic composite macrostructure, this limitation can be overcome by the new computational methodology we recently developed in the framework of this project. And this computational approach can be actually used to run very efficient simulation of real composite macrostructure, which are actually several orders magnitude larger than the models found in the literature, without compromising the accuracy of the results. To help you visualize the improvement in computational cost of these models, the common macromechanical models in the literature only contain a volume of few tens of fibers and requires a high-performance computing to run and complete. And even then, the simulation requires a few days to complete. On the other hand, with our new approach, a model can contain up to 2,000 or even 3,000 fibers and requires less than a day to complete using a personal computer.
So who are some of the other researchers working on this with you?
I have to say that this is a highly multidisciplinary research team from four different departments from two UK institutions, the Imperial College London and the University of Bristol. The nice thing is that actually we meet regularly in a weekly basis with the members of the same work package, but also we're working closely with other work packages on tasks actually that related together in order to receive or provide support. We all meet every month to present our work, monitor the progress of the individual activities, and exchange ideas about challenges that we are facing. So this is a nice way to be on top of the task, but also be sure that what we are actually working on is impactful, but also novel for the field.
And finally, where does the funding come from? Do you have any industrial partnerships?
Mainly this is a UK EPCRC project run, but we have an active collaboration with other universities and academic groups, such as the University of Southampton, University of Oxford, but also outside the UK, University of Vienna, the EPFL, and a few others. But apart from the academic collaborations with the universities, we have lots of industrial partners which supply the materials, but also advise us for the current needs from the industrial side. Just to highlight that in total, we collaborate with 19 companies. To give a small example of the breadth of the industrial partners, we collaborate with the National Composite Center, the Airbus, BAE Systems, Nexus, Solvay, and many others.
Well, thank you very much for speaking with us.
Thank you, Michael. It's nice being here.